that thanks for actually doing your job, Mr. Dilly Sticker. I would take that.
I would like print those.
We could make a bunch of those stickers, and I could get one every day that I actually do my job. And out of 180 days, I'd probably have like 125 of them. Yeah.
Congratulations, you put
Mr. Pope was making goals for himself before the school year started, and goal number 1 said make a list of goals, and then goal number 2 said check off something on the list. So he checked off the thing that said make a list of goals, and then he checked off the one that said, and then he actually made like do chapter 4 or whatever. So. Okay. He was probably more specific than that, but I don't care. It's physics. Yeah. Physics tries to use math in a relevant way. All right, so the big picture. There we go. Those last 2 chapters, chapter 3 and chapter 4, told us ways to look at quantitative data and categorical data. Okay. We only looked at a single distribution though. And when it comes down to it, looking at a single distribution is less interesting. We can look at a single set of data, but almost always comparative data is better. Comparative data is more interesting, right? Like looking at something that's happening now, like drug use in Zebra Woolly, right? If we had a graph that showed that, that in itself kind of interesting because it tells us maybe a little bit about what's happening now. But it is certainly better to take that and compare it to, say, the same set of data from 10 years ago. Because looking at a change over time tells us a lot of interesting things. How have things changed over time? And overall, we get more interest, we can answer more interesting questions when we have comparative data, when we look at different groups. And so we end up doing both. Nope, I try that every time and it doesn't work. Overall, we can do both, and we will do both, but the best kind of data is comparative, where we're looking at 2 different sets. And overall, when you're actually going to go out and do things with it in life, you're going to be more likely looking at comparative data. So hopefully you got a chance to read the book and start on your notes this weekend so you know a little bit about what's going on here. This is the average wind speed for every day in 1989. That is a single graph that has all of the average wind speeds. It's interesting, right? We can see a distribution that appears to be unimodal and skewed to the right. The thing about average wind speed, though, is that you're probably going to have vastly different wind speeds depending on what time of the year it is. So looking at one graph of all of the wind speeds, not super interesting. So what we're going to want to do to make it a more interesting graph is to break it up by time. So that's what I just said. There might be an outlier up there. We don't really know. The median daily wind speed is about 1.9. IQ bar is about 1.78. We know that the mean is going to be higher than the median in this case. So yeah, the question is this one down here. We think it's probably an outlier. It's so far away from the rest of the data that we think it's probably an outlier, but we haven't proven it. And so that's what we're going to do first here is there is a mathematical definition of what an outlier is, and we can calculate that. So the numbers that we have there on the right, those are the 5-number summary for that set of wind speeds. It's the medians, it's the quartiles, and the extremes, sometimes known as the min and the max. Notice again, there's that max that we think is probably an outlier. It's fairly far away from the rest, right? This is all 0.2 to 2.93. if you look at the difference between quartile 1 and the min, it's like a difference of 1. But a difference of the quartile 3 and the max, you have a difference of 6-ish, right? So we can see that this area over here definitely skews right because this difference is much higher than this difference, right? But is it actually an outlier? So let's make a box plot and check it out. Box plots are really nice when comparing groups. They are really good at pointing out outliers. Histograms, not the best at pointing out outliers, but box plots are very good for that. So here's the way you draw a box plot. You draw a single vertical axis spanning the range of the data. Draw short lines at the lower and upper quartiles, that space right there. And at the median, connect them to form a box. So there's the box portion of your box in the strip plot. By the way, vertical versus horizontal doesn't matter, okay? They do this vertically. When we make it on our calculators, the calculators tend to do it horizontal. Okay, thus far? Do my notes actually follow what we're doing today? It should be like the part of the box plot. And I think that last page is the one that was the top part. Yeah, it's box plots for all of them. But I didn't want to put box plots for the bottom two and like not fill that in and then do it for the top because then that gets the top one away, right? Takes away the mystery. And I know that that's the fun part for you guys. So I don't want to take that away from you. Okay, so what we want to do then is erect a fence. The fences are going to tell us whether or not something is an outlier or not. The fences, anything on the outside of these fences is going to be considered an outlier. You don't actually have to draw the fences on the table. Sometimes you're just kind of like, you notice how they do it here with like a dotted line? The dotted line here just kind of signifies anything on the outside. You don't have to put that in. A fence is 1.5 IQRs above the upper quartile. Brittany. That is always. Did I put the data on this slide? No, I didn't. Where's my? Here, somebody write those down. Write those down in your paper. I'm gonna do them on the other sheet there. Somebody got it? Okay, I'm going back. Oh, one more. Am I going the wrong way?
Yes, you are.
Ah! Okay. So what were my things? My max was 8.67, right? What were the others? 2.93, 1.90, 1.15, and 0.20. Okay. So it says here that the upper fence is 1.5 IQRs. And what that means is, first of all, we need to find the interquartile range. So we're going to take 2.93 minus 1.15. So 2.93 minus 1.15. That is my IQR. And let's see, what's that? Can I do that in my head? That's 1.78, I think, right? 93 minus 15 is 78. Yeah. Okay. So the interquartile range here is 1.78. That's the difference between the upper and the lower quartiles. Now, the fences are 1.5 IQRs above the upper and 1.5 IQRs below the lower. That's 1 IQR right here. So we need to find out what 1.5 IQRs is. So we're going to take 1.78 and we're going to multiply it by 1.5. I don't think I want to do that one in my head right now. I mean, it's just 178 times 15, but and I can do that eventually. But somebody tell me what it is. Calculators are faster. 3.36. Good enough. Alicia messed up. Let it be known on record. It's been recorded. 1.1, 2 point what? 6, 7. Alicia's got no, she's amazing. Is why. All right, 2.67 is what 1.5 IQRs is. So what this means is, if we were to take the upper quartile and add 2.67, we're going to get the upper fence. So 2.93 plus 2.67 equals what now? Don't ask Alicia. She can't calculate it. Somebody else calculated it. I mean, I could. I just don't want to. 5.6. So upper fence, 5.6. That's why this thing is right there. That's from here to here is 2.67, right? From the top of the upper quartile to the fence is 2.67. And then we're going to go down the other direction, 2.67. And then that's going to be 1.15 minus 2.67. I'm waiting. You got it, right? Negative 1.5. So that's what this is down here, negative 1.5. And so we've gone below that. So what the fences tell us is any data point above 5.6, there it is, 5.6 is going to be an outlier, and any point below negative 1.5 is going to be an outlier. So was that max, is this max here an outlier? Yes. Mathematically defined, it is an outlier. We know by calculating the fences that this is an outlier. Gentlemen. Absolutely, yeah. Like, well, if you want to calculate it just to make sure that the fence goes there. But like this one, yes, we will not have a lower outlier because it is impossible for us to have a negative. Right? Yeah, unless the wind is like becoming a vacuum somehow. Yeah. So maybe in space you can. What's up there? Yes. And you know, call it an outlier. Yeah. I don't know if there's a hard and fast rule. Again, you'll find a lot of things in statistics that kind of like it's pretty close. We should probably. The best thing to do is if you have one that's like on the line, just be like, this one is literally on the line, so we might call it an outlier, we might not. Right? Just the best thing you can do is to report the data as well as you can. Yeah, exactly. Be able to be a little wobbly. In your box. Yep. Anything else? All right. Oh, you can't read that now. Note, the fences only help with constructing the box plot and not should appear in the final display, right? Yeah. Typically speaking, what that means is you're going to use these fences to grow the whiskers. Even though the max is at 8.67, we're going to stop the whisker here at the fence. And that's our max. So there's our box and whisker plot, right? There's the boxes, there's the whiskers. And then for that outlier, what we do is we have special things for the outlier. So like when you guys did that box plot the other day, and you had that point out there, the points out there represent an outlier. And as it turns out, This one, that 8.67 is really far away. It's a far outlier, meaning that it was 3 IQRs away, and it still was beyond that. We had 3 other outliers in the data set that were actually, you can't really see in the histogram at all, but they're there. Brittany. Oh, yeah. Sorry. That one. I don't have anything else to say about this slide, so I'm just going to stand here awkwardly for a minute. Okay. I think that's good. Box plots do have that advantage of being able to see the outliers. Notice this particular graph right here. Looking at the histogram, would you guess that these 3 values right here were outliers? No, because they appear to be a part of the rest of the set. However, these 3 are beyond the max, right? They are beyond the fence. And so there's these values here that's an outlier. This one that we figured was an outlier is actually a far outlier. So you can kind of see in the box plot and the histogram kind of match a little bit. You can see that the bulk of the data, the middle 50% of the data, is right here in this big set. And 25% of that upper data is in this little upper 25%. And then this little bar and that bar, which make the bottom 25%, make it up there. In fact, you can even see the skewness in the graph, right? You can see the skew here. You can see the skew in this elongated whisker and outliers over here. What do you want, Mr. Pierce? No, you're not. Yes. Nita. Miss Nita. $10. And hey, I have a list of calculators that these guys have. You probably need that. I do. Okay, I'll give it to you. Yep. Now the D's gone. I lost track of what I was going to say. Oh yeah, skewness. You can see the skewness in the plot, right? You can see the histogram here. But when you have a whisker that's longer on one side and short on the other side, you can actually say that that's probably going to be a bit of a skew, because this being long and that being short means that there's more data being, that same 25% of the data is pushed out further this direction, right? So histograms are good. They show us shape. Box plots, great for showing outliers. They kind of show its shape a little bit, but not like perfectly. But you can definitely see the skewness, right? A long whisker versus a short whisker means it's going to be skewed to the right. I just want to do a couple more slides. Comparing groups. Like I said, more interesting to always compare groups. This is that same data split into fall versus winter, spring, summer versus fall, winter. You can then better compare what's happening throughout the year. Where are we more likely going to have higher wind speeds? How many say fall, winter? How many say spring, summer? Fall, winter. Look, spring, summer has a huge amount over here, but remember, this is frequency. This is how many are they showing up. There's 50 days that have like around 1.0, which I forget how they measure this. I think 1.0 is like 10. So notice that there's a big grouping of them on the low speeds in the spring, summer, which means not super high wind speeds in the spring, summer. Whereas you can see a more data occurring over here in the 2.0 to 4.0 than there is over here, which means this one is going to have higher wind speeds. This one certainly has a higher skew to it, a much bigger skew to it than this one does. But it's got more data over here. So comparing the two, we can see that. In fact, if you spread it out even more, month by month, this is a box plot of every month, January to December. Have a quick little conversation with somebody next to you, and just talk about where we would likely to see high wind speeds, low wind speeds, etc. Can you do that for me? Talk about high wind speeds, talk about low wind speeds, and talk about what you think the outliers mean. Okay? Have a quick 1 minute conversation. Big outliers. All right, finish that conversation in the next 20 seconds. And let's just quickly go group to group. Tell me some of your observations about high speeds, low speeds, what the outliers thought, or just maybe anything interesting that came out of that. So we'll just start in the back group up. So back group right there, you 6. November had high wind speeds. And how do you know that? Okay, so it looks kind of like it's got the highest median. So there were 3 days that had some pretty serious wind speeds there, yeah. Looking across, let's see. I can't do the straight line things. Let's try it here. I mean, I'm trying to be as fair as I can. Is that better? Is that better?
If you put a line between those two, you can get one.
Okay, so yeah, but the straight line is somewhere around there. So in terms of median, what are the other months that have close medians to that? January, March, February is a little low. They have a lot in the top 50%, but it's medians down there. Okay, so then let's take November's max. Hey, it's not, you do it. It's not easy making a straight line. So November's max, so it looks like November and March have really similar months, right? Their medians are really close and their maxes are really close. Is November the highest though? No, what's the actual highest? Looks like January. Because their medians are about the same in height, but January's has a higher max. So that means that the top 25 or the top 50% of the data for January and the top 50% of the data for November, January's goes up higher. So we'd probably say that January's got the highest there. But November is definitely close. And same with March. Like March is like practically the same month as November. Justin? Well, I mean, it's that plus these here, right? The whole thing makes up 100%. Usually there's only like 1 or 2 outliers. So when we say 100%, we're like, it's like 99% of the data with the outliers being noted. Yeah. Good. We talked about that one for a while. I might have taken other people's observations. But back there in the group, back there. What's that? Don't fly kites in July. Yeah, that's probably a good choice. July, right here. It's funny that July has an outlier that's like below November's median, right? July is not a very windy month, which probably explains why July is also typically the hottest month, because we don't get much wind, right? Other observations, middle group? Okay. Yeah. What were these outliers? More than likely, what were these outliers? Storms. They're probably a storm. This one was a doozy of a storm, right? Because it was 3 interquartile ranges away. It was reaching speeds of like 80 some odd miles an hour. That was probably quite a storm, right? And I think in the book, they give you the year that this data was taken, and they actually tell you what storm it was too. I don't remember. Front groups, any other observations to make? Yeah, very much so. You can see your seasons, fall, spring, summer. Fall and spring are very similar, and then winter, yeah, definitely. Definitely. Yeah, there's a lot more. There's a lot more outliers that we can see when we split it up by month. Outliers for that month that show up in the data here. Yeah. Any other observations from anybody? Things that we can say about this particular graph? Wind speed, things, information we can glean from it. We can make a connection to our trigonometry. Anybody see the connection to trigonometry in this graph? I think it's in 10. Tsunami is a wave. Yeah. Hurricane. Yeah, it could very well have been a hurricane. Hurricanes, I think, usually get above 100, though. I think. Yeah. But it might have been a hurricane. Yeah, it could be. Connection to pre-calculus, wind speeds tend to follow a season that is sinusoidal. Right? They tend to make a sine graph. Temperature does the same thing. It makes a sinusoidal graph. I just like saying the word sinusoidal. I think it's a fun word. Also, the tides tend to follow a sinusoidal graph. Those are all things that tend to follow the season. So you end up with that. All right. What did they tell you? We just talked about that. Okay, that's all we want to do for today here. Can you grab your calculators? I'm gonna get. Nope, I said keep. I wanted to get rid of them. Oh well. We're gonna stop the video.